Artificial intelligence will completely transform our world. But what is AI? Why will it affect you? And how can you and your business survive and thrive through the AI revolution? Welcome to AI and You. Here is your host, author, speaker, and futurist, Peter Scott.
Welcome to episode 65. For those of you just joining us, I'm Peter Scott, and I love to help people understand AI, starting with myself, because it is a bottomless topic. I will never be done with asking questions about AI and finding out the answers, and I suspect it's going to evolve faster than I can catch up with it. Maybe I'll need AI eventually to help me understand it. Less than half kidding about that. Today's interview is going to be a treat because you know that neuroscience is near and dear to our hearts here at AI and You, and the main reason for that is that so far we have not created artificial general intelligence, but our advances in AI in that direction, primitive as they may be, have mostly been along the lines of emulating how we think the human brain works. So the better we get at understanding what's on top of our necks, the better we might be able to make AI that can do general kinds of tasks. Professor Olav Krigolson is a neuroscientist. His Twitter handle is @ThatNeurosciGuy at the University of Victoria, where he runs the Theoretical and Applied Neuroscience Laboratory, most commonly known as the Krigolson Lab. He has developed a unique mobile electroencephalography EEG to you and me system to investigate what's happening in our brains when we're tired, stressed, oxygen deprived, struggling with dementia, concussed, or on Mars where it might be all at the same time. And he's done that at the Hawaii Space Exploration Analog and Simulation, or HI-SEAS, environment, which, unlike most of the rest of Hawaii, is a bleak, barren landscape on Mauna Loa, where the altitude and the rocks and the general lack of living things conspires to create an environment somewhat like Mars, although obviously with much more atmosphere and much warmer. But it's a place where people can get together and be relatively undisturbed while they simulate what it would be like to live in a Mars habitat. And Olav has used EEGs and analyses of their brainwaves to look at how people in that environment fared under conditions of stress, etc. So let's get right on with the interview with Olav Krigolson. Olav, welcome to Artificial Intelligence and You.
Hi, Peter. Well, thanks for having me.
Well, neuroscience is near and dear to the hearts of AI people, as I was explaining in the introduction. And when I was in high school, neuroscience wasn't on the menu. We were basic chemistry, biology, physics. Neuroscience would be something that you'd have to decide to specialize in later on. How did your journey from, say, high school take you into that field?
That's a great question. One of my claims to fame as a neuroscientist is I never took high school biology. I actually did physics and chemistry. The first biology class I hit would be called a neuroscience class. So I was in grad school and I was looking at sort of the elective courses that were available to me for the program. I was actually going to do a master's degree in kinesiology. And one of them was a neuroscience course. And I took the course and I was absolutely fascinated. I was interested in learning and how people learn and how people make decisions. And here was this course that was telling me about what was going on in the brain when people learned and what was going on in the brain when people made decisions. I was just fascinated and it hooked me. So that led me to a PhD in neuroscience and a postdoctoral fellow in neuroscience.
Great story. And have you put your own brain under the microscope in the course of your work?
I have multiple times. I've had my brain scanned with fMRI a couple of times. And I've had EEG measured in the lab multiple times. And now with the mobile technology we use, I measure my brainwaves almost every day. And I've even fired magnetic pulses, transcranial magnetic stimulation into my brain to give myself a temporary brain lesion.
Wow, that sounds like it's carrying the commitment a little far. How do you know that it's temporary, and why were you injuring your brain in that way?
Well, it is temporary. There's a lot of research that was done on transcranial magnetic stimulation, or TMS. In fact, it's used now clinically. Certain clinical neuropsychologists will use TMS to treat depression. So you could go to a clinic and it's a viable treatment. But basically, the idea is a magnetic pulse disrupts the brain function briefly, and then things return to normal. And why I did it, I had a fellow colleague that had one in his lab. He was using it to study if you took out parts of the brain, how that impacts human movement. So he wanted to know if I wanted to have my brain temporarily fried, I guess. So I did. It was quite the experience.
This is your brain on TMS. I know there's no nerve endings in the brain. At least that's the common saying. So I assume it didn't hurt, but did you notice it?
You do notice it. The classic TMS test is they hit Broca's area, which is associated with speech production. So imagine I'm talking to you and we're having a conversation. All of a sudden, if you turn on a TMS pulse, a regular pulse to Broca's area, you lose the ability to speak. So your body is generating sound. What Broca's area specifically does is turn words into a very specific pattern. So what you hear is sort of like a, because your mouth is moving and sound is coming out, but it's not the words you intend to produce. And what's very trippy about it, if you will, is that you were intending. So classic, you could imagine you count from 1 to 20. So you go 1, 2, 3, 4, 5. And then they turn on the TMS and you go, and then they turn it off and you go 10, 11, 12. And then they turn it back on and you go, So it's quite an interesting experience because you're trying to speak and you just literally can't.
Wow. I had no idea we were going down this road. Just so we're clear, for completeness sake, people applying to be grad students in your lab, is this something they should expect to be asked for?
No, my lab's safe. We don't use any invasive techniques like TMS. I was just visiting a friend who had that particular technology, and I was always curious about it. So he played around with it with me for a bit.
Okay, so no giant yellow warning signs on your lab saying, warning, transcranial magnetic field, keep head out, or...
No, we do have one because we do have some biohazard material, but that's related to do with genetic prototyping. So we take swabs from people's mouths to get a genetic expression, and that requires the university, at least in their world, would say that's a biohazard. So we have a special room where we have to keep the samples and protocols. But generally what we do is just put some electrodes on your head and measure your brainwaves.
All right. Now, in that, you've got some specialization, and I know from your TEDx talk that you are able to look at people and tell whether they are too tired on an objective scale, much more useful than asking, are you tired? Can you talk about that research?
Yeah, of course. It really started with the advent of mobile technology. So back in about 2012, I was approached by a Canadian company, Interaxon, and they were developing a mobile EEG system. So most people think of EEG with a whole bunch of electrodes on the top of the head and a hospital or at least a research lab. And they approached me with a little headband that only had 4 electrodes, and they were curious whether it measured brainwaves or not. So we did a lot of background work to make sure it did measure brainwaves, and lo and behold, it did. So we were quite surprised, but we've all seen virtual reality get cheap and affordable. We've all seen all manner of technologies go this route. So we started asking ourselves a question. If you can measure someone's brainwaves anywhere in 5 minutes, what can you do with that? And we've taken on a bunch of projects, but the fatigue project was an offset of that, which is it's been quite well established in the EEG literature that you can measure fatigue with brainwaves. But what's not as well established, well, what was impossible really, was to do it quickly, to do it in a couple of minutes. So we thought, can we build a mobile fatigue assessment device? So that's what we did. Our first sort of study with this was just classic basic science, I'd call it. We measured people with the big system, our medical grade EEG system, and we measured them with the portable system. And we got similar results. When we saw that they were tired with our $100,000 system, we saw the same pattern of results with the low cost mobile system. And then what actually happened is I went to the Consumer Electronics Show in Las Vegas, and I got to give a presentation on the main stage for the Digital Health Summit. And I was talking about the tech, and that led to all sorts of doors opening up. So we've done some work in a hospital environment. So we looked at doctors and nurses in the emergency room to see if we could detect fatigue. And lo and behold, we could detect fatigue. And we worked with heavy industry in northern BC. I can't mention the specific company, but they were very interested in fatigue in the workplace, and we were able to deploy the tech there. And I guess the one that we're kind of known for is I spent a week in the Mars High Seas habitat as a proof of concept for a NASA grant project where we wanted to show that we could measure fatigue in astronauts in a simulated environment.
Right. And we'll very much want to talk about the NASA experiment in a moment. But I want to backtrack to a Brainwave 101 kind of question, because I look at my brainwaves with one of the headsets, like you mentioned, and looks like a spider had a heart attack on the paper. I get that there's patterns in there that you can find, and you can say, these patterns look like this group. Okay, this patterns look like this group, and that's how you decide someone's tired. But how did they get trained in the first place? How do you know that that pattern means tired and not aroused, or not bored, or another state? How did you decide that that general pattern means tired?
Well, this is an area that needs a lot more research, actually. One of the problems with EEG findings, if I'm being honest, is that in some instances, there are multiple interpretations for the same pattern. Now, as we move further along and we build better classifiers, when I started doing this, we didn't use machine learning approaches. It was all just, we would look at specific bumps in the EEG signal. So a classic one we look at is called alpha. There are neural oscillations between 8 and 12 hertz. And generally, when people are tired, you see an increase in alpha power. But the problem is alpha power can increase for any number of reasons. So where it's heading is the classifiers are able to sort of separate patterns that look on the surface to be very similar, but there are subtle differences. So what we do is we look for truth data sets, we call them. So a data set where we know that all things being equal, the only difference between data set A and data set B is fatigue. So we match for any number of factors to control for other things, arousal, what you had for lunch, how much you slept last night. And then we build the classifiers on those data sets. And they're not perfect, but it's a step in the right direction. So as the technology improves, the hardware, the software is going to improve as well. So people are constantly improving the mathematics behind the classifiers, but we're also going to constantly improve the data we put through them.
Right. And so you mentioned a study or research that you did about using this technology for potential Mars explorers. Tell us about that.
Yeah, well, the Mars mission is going to be a very unique thing for NASA. So NASA is working under the assumption they're going to Mars. They've been told that by 2 sequential presidents. So they're planning for a Mars mission. And the biggest problem on a Mars mission is the crew is fairly autonomous. You know, when they went to the moon, the reality was they were in live communication the whole time and everything could be troubleshooted from the ground. On a Mars mission, they're going to be either out of touch or at least have severe communication lag for extended periods of time. So it means the crew has to operate independently to a large extent. And one of the things they're worried about is you can put a heart rate sensor on and know if someone's heart rate is higher than normal, and you can measure blood pressure. But what's the gold standard for measuring the brain? Like, how do you know if someone is ready to go outside, say, and do a Mars walk? So there is an open call on the NASA website. They reach out and they have research calls for solutions to brain health and performance. So how do we monitor brain health and performance? So me and a couple of colleagues realized that this mobile tech could be used to potentially do that. So we made a pitch and we ended up with a week in the high seas Mars habitat on the Big Island, Hawaii. It's used by NASA crews for Mars simulations. It's used by crews from the European Space Agency working on projects. And we got in there for a week. It's basically a dome on the side of a volcano. It's built to the specifications and size that they think that they would be able to build a housing unit on the surface of Mars. But it doesn't look much like one. There's 2x4s that are visible inside, and it's essentially a large tent in some things. But it does simulate the size and space. And it also, more importantly, simulates the psychology of it in the sense that every time you go outside, you have to wear a spacesuit. Communications are lagged. You live off of freeze-dried food. One of my particular favorites is you get about 60 seconds a day of water for showering, but you're exercising 4 hours a day because that's what astronauts do. So we spent a week in there, and the whole goal was to see if we could use our tech to track our brain performance over the week and to see if we could detect fatigue. In particular, we were really focused on cognitive fatigue for this first one.
And are you heading down a road where NASA will end up incorporating EEG sensors into the spacesuit helmets?
That's exactly where we're heading. So the follow-up to the initial mission was going to be a longer 1-month mission to really get into it. COVID got in the way of that, like it got in the way of everything. So we're going to go back as soon as we're able to schedule it and get back to Hawaii. And that's the hope, is that that data will then be used to get a larger NASA grant And then the idea is that what they do is they get lots of submissions for these projects. And then they, much like a science fair, they pick the best one. This is the tech we want to go with. But my hope is that the tech and the algorithms we're developing will end up on the ISS and then hopefully one day on Mars.
NASA's not going to be the only people on Mars. Have you had any talks with SpaceX?
We haven't yet. That's one that's on our to-do list, is to start exploring who else is interested in the tech. And to be fair, this idea of fatigue assessment, we've had a lot of conversations with airlines, heavy industry, trucking, any field where cognitive fatigue might impact decision-making or performance. People are kind of interested. One of the differences with our approach is that a lot of the existing approaches rely on continuous monitoring. So the sensors are on the whole time. Our assessments take about 2 to 3 minutes. So it's a case where you put on the device, you do the assessment, and then you're deemed good to go or not. So if you think of the airline example, the pilot would do the test before they get on the plane. And if they get a pass, then they're deemed to be not fatigued and they can fly. If they are fatigued, then potentially that's a down check and another pilot flies the plane that day.
Sort of like a breathalyzer for the brain.
That's exactly the way I envision it and think of it. It's just a quick brain breathalyzer.
Now, I want to talk about the links between human cognition and computer cognition here to bring in the AI angle some more, because there's this pervasive notion in AI that we're modeling the human brain. In fact, it's almost a subconscious assumption. And I question that assumption at times. And yet our models of physical computers look radically different from everything I know about the human brain. The physical computers have a processing unit, a separate memory area, and a way of getting information in and out. They have separate programming and execution phases. Human brain, at least to me, looks like one large lump of jelly where there is no separate memory and processing, no separate programming and execution phases. Horrible oversimplification, I know, but do you have anything to say about perhaps untangling some of those parallels?
I do, and we do some work with this in my lab. As you know, we actually use computational models, a form of AI, like a very simple form of AI, to make predictions about neural responses. But where it's going is not so much the hardware side, but the software side, which is building neural networks that are designed to mimic the brain. The problem, of course, is that the size of the neural network you would need to capture the entire human brain would be massive. So, very simple neural networks are on our phones that learn the pattern of our face and know to unlock the phone. We use them in the lab for very simple things. But to mimic the whole brain is quite a massive undertaking. Now, there are groups that are looking at that problem, that are trying to actually build a neural network that would have the same number of neural connections as the brain itself. I don't think we're there yet, but we've seen the power of these things. Now, where it gets interesting is how accurately it compares to the human brain. I call it biological plausibility. I actually supervised a PhD student a couple of years back who was in computer science, who had come up with a computational model that learned to perform a task, and it learned a lot better than a human. He'd made some changes to the model, and this thing could learn extremely quickly to perform this task. But my question to the student was, well, this is an impressive technological programming feat, but it doesn't tell us anything about the brain, because the brain can't learn that quickly. Like, we know that. Humans doing the same thing can't do what your algorithm can do. So the big question on the neuroscience side is, and there is an entire field called computational neuroscience, the big thing is always biological plausibility. How well does your model align with what happens in the brain? And there are people that do that. Definitely the neuroscientists that are using computational or AI simulations at the lowest level, so single neurons, have put a lot of work into making sure that their model holds up to what you actually see in terms of a neuron firing, if you will. Where it gets trickier, of course, is how does that scale up? And as I mentioned earlier, current computers can't handle enough simulated neurons to capture the entire brain.
But even at the lowest level, there is something called the Open Worm project I've heard of, which is attempting to simulate the neuronal structure of a nematode worm, which has 302 neurons. And the last I heard, they were still not connecting that to anything that demonstrated the behavior of a nematode worm, which doesn't bode well for going to larger scale organisms.
No, it's a challenging problem. But some things do work. Like, one of the things we do is when people learn, one of the ways they learn is through what I would call a prediction error. It's a difference between your expectation of what's going to happen and the actual outcome. So imagine you hit a tennis ball, you have an expectation of what's going to happen, and then there's what actually happens. And if there's a difference, we call that a prediction error. It's a key principle in reinforcement learning. Now, it turns out that if you measure with EEG the response to feedback in a simple gambling task, so you get people to play a little gambling game, the pattern in the EEG results parallels the pattern you see with the computational model that uses prediction errors. So when the model predicts you should see a large prediction error given the outcome, then we see a large neural response. And when the model predicts we should see a small prediction error given the results, we see a small neural signal. So we can come up with these sort of computational models that parallel what we see. They're not perfect, but at least the pattern is there. So I do think we're on the road to something. And in fact, this prediction error thing is big in our lives. If we have a robot vacuum, I bought a Roomba recently, and that's literally the key algorithm in these things is when you bump into something, that's a problem. So change your behavior and do something else.
You mentioned prediction there several times, and I've pulled a quote off one of your papers or websites where you said, when people make emotional decisions, you get a lot of activity in emotional parts of the brain, and that correlates with irrational decisions, while a more active prefrontal cortex is associated with more logical, rational choices. You can actually use this in a predictive fashion. To predict what?
I'll give you an example. There's a classic game that economists like to play. It's called the ultimatum game. And the ultimatum game works very, very simply. I have $100, and my only job is to share some of that money with you, Peter. So I have to make a decision. I'll give you 50, and I keep 50. So we walk away with whatever the share is, assuming you say yes. Your only job is to say yes or no, right? And one of the key rules to the ultimatum game is you only play one time. So it's your one crack at this. So the original research was done by a group from Princeton in Grand Central Station in New York. And they would just pull two strangers together, make sure they didn't know each other, and then they'd give them the money and the offer was made. And if it was yes, you took your money and walked away. And if it was no, then no one get any money. But that's the other feature is that if you say no, no one gets anything. So most people do 50-50. But there are people that they think, well, hey, I'm going to keep 90, you take 10. Now, logically, you should take $10 because $10 is better than nothing. But what does human behavior show us? 70% of people say no to that offer. They go, nope, I'm not doing this. Now, if you're going to play more than once, that's actually a rational choice because you're basically saying, well, if you screw me over like this, I'm going to keep doing this and no one else is going to win. So you're sending a message, treat me fairly or else. But if you only play one time, you should take the money. Now, the neuroscience of this is interesting. If you do this in an fMRI scanner, the people that accept the $10 have more activity in the prefrontal cortex than they do in the emotional parts of the brain. And the people that reject the $10 and reject the offer and get zero, they have more activity in the emotional part of their brain than they do in the prefrontal cortex.
They're going, it's worth $10 to teach this guy to not be a jerk.
Exactly. So what you can see is this pattern of results where the brain activity predicts what someone's going to do. And of course, the brain activity is in advance of them actually responding. It's not after the response, it's before.
So you can see from the brain scan what they're going to do before they say it.
Yeah, it's a very interesting field. There's a lot of very interesting work that's being done with real-time fMRI. That people are using it for image prediction. So they show you a picture of a house or a car and they know what you're looking at.
Well, you can go straight from this to more controversial things like lie detection. Someone strapped to an interrogation chair and has one of these on their head. Or you said needs an fMRI, so they've got to be lying on a table.
There's work being done with EEG in this area as well, but that lie detection's already been done. There's a published study where they were showing people pictures of a room, and either you'd been in the room or you hadn't been in the room, and they could tell whether you'd been in the room or not. Now, where I'm going with this is you could imagine taking this to a court of law. You show a picture of the murder scene to the potential murderer, and their brain is saying, yes, I've been in the room. Well, the idea is that would mean you're guilty.
Right. I remember a fiction book by Daniel Suarez where a guy was kidnapped by some people with advanced tech, and the point was that this wasn't that advanced, but they wanted information out of him and they put him in an fMRI scanner and asked him for his password and said, is the first letter A, is the first letter B? It was just a machine doing this. And it noted when the scan spikes, it said, okay, now is the second letter this? And from what you're saying, we could do that now.
It's close. The biggest problem is accuracy rates. To publish a scientific paper, your accuracy rate doesn't have to be 100%. It's got to be about 70% or lower, possibly. But it's getting there. And we actually just published a paper with a colleague of mine, Alona Feisch. She's at the University of Alberta, where with EEG, we were able to determine what words you were seeing on the screen. So we'd put up a series of words and we were able to separate that using a machine learning approach. But there was enough information in the EEG signal to tell you that you were looking at the word turtle versus the word dove or something like this.
That's the end of part 1 of the interview. Part 2 will be next week. At the time I'm recording this, it's the centennial of the birth of Gene Roddenberry, the creator of Star Trek. And NASA just aired a panel on diversity with his son and George Takei, who was Sulu. And with me being a Trekkie, I was very much into that. But you may ask, what's that got to do with AI? Well, if you've listened to much of this series, you know that there's a lot of Star Trek connections to be made with AI. So I thought I'd mark that centennial by bringing up a few of them. And this is getting further out into the future here in the speculation, but just because it's a long way off doesn't mean that there aren't some things that we can predict fairly accurately. We know that one day the sun will turn into a red giant. We know that with complete certainty. But long before then, we will have to solve the problem of how we get along with AI. Once it becomes super intelligent, of course, there are projections that it might wipe us out. But some of the more optimistic ones include it taking care of us like pets, like in, say, a Wall-E movie where we are just laying back on our lounges while everything is taken care of for us. Now, if you're Homer Simpson, that sounds pretty good, but for most of the rest of us, it's rather horrifying. And yet it is hard to come up with a plausible scenario that is better than that. Once artificial intelligence becomes super intelligent, what are we going to do when AI can take care of everything for us? And I like to think that Star Trek shows us the best, most fully fleshed out, most relatable example of what that best alternative could be. That we're learning, growing, doing good things in the universe. And that most of all, we had earned the right to be there doing those things because Star Trek showed us having evolved to be a humanity that valued life in all its infinite diversities and infinite combinations. That very much contrasted with where we were when the series was conceived and where we are now. You could trust the universe and the species in it to Kirk and Picard and Spock and McCoy and Scotty, but we haven't gotten there yet. Only in a few places, not enough. Now, yes, you can say that's not exactly an accurate future because, for one thing, it doesn't include artificial superintelligences at nearly the scale that is 99% inevitable by that point. So yes, even in the most optimistic scenario, it's going to look different because of AI. But the point is, we need to be the kind of people that can be trusted out there. One of the ideas about our future with superintelligent AI is that it might choose to keep us in a simulation as a way of satisfying our desires while keeping us safe. But what if it were not just keeping us safe from ourselves, but keeping the rest of the universe safe from us? And if you really want to go full tilt tinfoil hat, then you could say, well, what if that has already happened? And we are in a simulation right now because the AI is keeping us there until we've demonstrated that it's safe to let us out. No, I don't really think that. Or at least if you think that you're trapped in a perfect simulation, then your actions and beliefs should be identical to what they would be if it were reality. It only makes a difference if you think you can escape. But if you do think we're in a simulation, then maybe you should work on helping the human race evolve to the point where it's mature enough to be trusted around other species. Because maybe that's the criterion for being let out. Now, all of this talk about Star Trek-like futures is obviously way off in the future, but we have a space program right now. And periodically we hear these same ludicrous arguments about why are we spending all this money on space when we need it on Earth. And firstly, just because it's concentrated in a few spectacular rocket launches and other things, that doesn't mean that it's a lot of money. The United States has spent less on NASA throughout its entire lifetime since the program was started than it spends every year on the military. The NASA budget is less than twice what Americans spend every year on snacks and supplies for Super Bowl parties, and you don't hear them say, maybe we should cut back on that and give it to the poor instead. There is more to our existence than just taking care of our most pressing problems and nothing else. Otherwise, why climb Everest? Why write a symphony? Why hold the Olympic Games? And many of us don't do any of those things, but we don't begrudge the people who do. And the same is true of space. I suspect I'm preaching to the choir here, of course. But even though every dollar invested in space development is returned sevenfold in advantages from developing technology, because virtually everything that is done in space is the first time a one-off of some kind, not like building the same bomb over and over again to blow it up. Some people still think it's frivolous. And yes, there are more reasons to go into space than just return on investment in high technology, because if you wanted that, you could probably find other ways of doing it. We do this because we need to become a multiplanetary species. We need to be independent of the Earth. And that sounds so very science fiction-y because it's so very far off. But if we don't start, we'll never get there. This is where we need to start. And you have to have a good imagination to see where it might lead us, because at the moment we're restricted to trying to build a few domes on Mars, maybe an outpost on the moon, neither of which are very appealing places to live on. Sometimes I wish we'd grown up in a globular cluster where the stars are so much closer together and there would be a chance that an interesting planet would be a lot closer to us. I've read that, although it was thought until recently that there was a small likelihood of there being inhabitable planets in a globular cluster, that is no longer thought to be the case with some new observations. So we're stuck with the closest star being over 4 light years away. It's a pity. It would have given us a lot more incentive to develop space travel that could go further if we only had a third of a light year to go to the next solar system. But some people think that the goal of establishing an independent colony on Mars, for instance, isn't a good idea. And they say that we should instead focus on putting that money, again, with the argument about the money. I want to bring up that meme that says, why not do both? But to put that money into keeping Earth habitable. And they think that as long as we have another colony somewhere else, then that removes the incentive for us to take care of the Earth. This is a silly argument. Suppose you went to your bank and you got to chatting with the IT officer there, and he said, we don't keep backups of your data, and we're not into this cloud thing either. There's just one copy of it, the live copy that's in our central mainframe. But we think that because of that, it incentivizes us to take really good care of that data. It's only one place that we have to look now, and so we're going to take extra special care of that one place to protect it, much better than would happen if we were spreading our resources. Are you going to keep your money there? No. The next words out of your mouth are going to be, I'd like to make a withdrawal, all of it. So if it's not true for your bank account, why should it be true for the human race? And the people who make that argument about needing that motivation aren't thinking about who needs to be motivated. It's not them that needs the extra motivation. They've already got enough. They're thinking about other people that need to be motivated to take better care of the Earth. But those people don't look at anything that they can't see beyond a year out, so it won't make any difference to them. But let's say that you did take all of the money that we're spending on space and spent that on the environment and mitigating global warming and pollution and every other kind of man-made damage to the Earth. You could do all that only to have the human race wiped out by something that wasn't even our fault, like a massive coronal mass ejection or the explosion of the Yellowstone supervolcano or the reversal of the Earth's magnetic field. There are several ways that the human race could be wiped out on Earth by something that we have no ability to control. But there are very many fewer things that could do that if we were also on Mars. So again, it only makes sense to have a backup location for the human race. And God bless the people who are looking forward to living on Mars, because it's going to be hard and it's going to be rather monochromatic, but we need them. So today's space program is the very first steps on a very long road towards a possible Star Trek-like future. And I thank Gene Roddenberry, who would have been 100 years old now, for giving us that vision. I actually went to his memorial service, 1991, Forest Lawn. No, I was not one of the Trekkies that showed up in costume. I wore a suit. It's a memorial service. But it was very tasteful. The service itself, there was a bagpiper because he was an ex-police officer, and there was a missing man flyover with Beechcraft Starship experimental light planes of a rather radical design. Because, at least as far as I'm concerned, the Star Trek that he and, of course, so many others gave us was the clearest goal for what we need to do to coexist successfully with advanced AI, however many years in the future that happens. In today's news ripped from the headlines about AI, Google has introduced a conversational search engine called Lambda. There's no B in there. It stands for the language model for dialogue applications. And it is, as they say, their first steps in taking search from a stateless to a stateful conversation, where you ask a question, it gives an answer, and asks other questions to clarify what you want. That, of course, is huge. And they did that by training Lambda on dialogue rather than single question-answer exchanges. Of course, it's using transformer-based language models, as just about anything to do with NLP does these days. Next week, we'll conclude the interview with Olav Krigolson, when we'll be talking about many more things about neuroscience, including the structure of the human brain and how it's organized. Until then, remember, no matter how much computers learn how to do, it's how we come together as humans that matters.
That's all for this episode of AI and You. Please leave a rating and comment and share with your friends. Get the book Crisis of Control and see more videos and articles at aiandyou.net. That's aiandyou.net, where you can also send us your questions. Thank you for listening.